We have frequently heard colleagues express the view that decision trees are a solved problem. We do not agree with this proposition and will close with a couple of open research problems. Stable trees. It is well known that the error rate of a tree, and the cases from which it was constructed, the resubstitution error rate is much lower than the error rate on unseen cases, the predictive error rate. For example, on a well-known letter recognition dataset with 20,000 cases, the resubstitution error rate for C4.5 is 4%, but the error rate from a leave one out 20,000-fold cross-validation is 11.7%, as thus demonstrates leaving out a single case from 20,000 often affects the tree that is constructed. Suppose now that we could develop a non-trivial tree construction algorithm that was hardly ever affected by omitting a single case. For such stable trees, the resubstitution error rate should approximate the leave one out cross-validated error rate, suggesting that the tree is of the right size. Decomposing complex trees in sample classifiers, whether generated by boosting, bagging, weight randomization, or other techniques, usually offer improved predictive accuracy. Now, given a small number of decision trees, it is possible to generate a single, very complex tree that is exactly equivalent to voting the original trees. But can we go the other way? That is, can a complex tree be broken down to a small collection of simple trees that, when voted together, give the same result as the complex tree? Such decomposition would be of great help in producing comprehensible decision trees. Limitations of a k-means algorithm. In addition to being sensitive to initialization, the k-means algorithm suffers from several other problems. First, observe that k-means is a limiting case of fitting data by a mixture of k-Gaussians with identical isotropic covariance matrices, that is, sigma of delta square times the identity matrix, where the solved assignments of data points to mixture components are hardened to allocate each data point solely to the most likely component. So it will falter whenever the data is not well described by reasonably separated spherical balls. And for example, if there are non-convex shaped clusters in the data. The problem may be alleviated by rescaling the data to whiten it before clustering, or by using a different distance measure that is more appropriate for the dataset. For example, information theoretic clustering uses the KL divergence to measure the distance between the two data points representing two discrete probability distributions. It has been recently shown that if one measures distance by selecting any member of a very large class of divergences called fragment divergences during the assignment step and makes no other changes as the essential properties of k-means, including guaranteed convergence, linear separation boundaries, and scalability, are retained. This result makes k-means effective for a much larger class of datasets so long as an appropriate divergence is used. K-means can be paired with another algorithm to describe the non-convex clusters. One first clusters the data into a large number of groups using k-means. These groups are then agglomerated into larger clusters using single-link hierarchical clustering, which can detect complex shapes. The approach also makes the solution less sensitive to initialization, and since the hierarchical method provides results at multiple resolutions, one does not need to pre-specify k either. The cost of the optimal solution decreases with increasing k till it hits zero when the number of clusters equals the number of distinct data points. This makes it more difficult to a. Directly compare solutions with the different numbers of clusters, and b. To find the optimal value of k. If the desired k is not known in advance, one will typically run k-means with the different values of k, and then use a suitable criterion to select one of the results. For example, SAS uses the cube clustering criterion, while X-means adds the complexity term, which increases with k to the original cost function, equation 1, and then identifies the k which minimizes this adjusted cost. Alternatively, one can progressively increase the number of clusters in conjunction with the suitable stopping criterion, and bisecting k-means achieves this by first putting all the data into a single cluster and then recursively splitting the least compact cluster into two using two means. The celebrated LBG algorithm used for vector quantization doubles the number of clusters till a suitable code book size is obtained. Both these approaches thus alleviate the need to know k beforehand. The algorithm is also sensitive to the presence of outliers, since mean is not a robust statistic. A pre-processing step to remove outliers can be helpful post-processing the results, for example, to eliminate small clusters or to merge close clusters into a large cluster is also desirable. Ball and Hall's ISO data algorithm from 1967 effectively used both pre and post processing on k-means.